Hello everyone, welcome back. So, last few classes we have been discussing about the governing equations. We derived the mass conservation equation, we derived the momentum conservation equation, and we also saw what happens to these conservation equations in the limit of Mach tending to 0, that is basically the incompressible flows. And we have been discussing that for incompressible flow the energy equation is not that important. Because you do not have change in temperature or the density, okay. But for the compressible flow energy equations become very important. Okay. So, in today's class we will be discussing about the energy equation, we will briefly derive it, we will look at different forms of the energy equation, and after that we will look at all the equations mass, momentum, energy in one matrix form, and we will see how we can utilize these equations for solving our CFD problem. So, let us start with the energy equation. So, using the Reynolds transport theorem we had, okay, you can also derive the integral form of the energy equation, just you replace the B term. So, if you recall the Reynolds transport theorem, we had the extensive property, intensive property, and per unit mass was the intensive, and the total property was the extensive property, and we did for mass and the momentum. Similarly, you can do for energy, and you will find the expression for the energy. Before going there, let us go to the kinetic energy equation, which is nothing but the extension of your momentum equation. So, if I write in a very compact form, okay, so dui by dt, that is the mass into acceleration, is equal to del by. So, this is the total derivative, okay, del by del x j tau y j and plus rho v I, right. And if we just multiply this entire thing by say u I, okay. So, as we have been discussing that in the Einstein notation, when you multiply when there is a repetitive index, it automatically means summation also. So, you can write it in terms of rho u I du I by dt, the smaller one would be basically this will be u I del by del x j tau I j plus rho u I b I, right. So, this is in your the tensor form. If you want to be simple, you could also like you can take u multiply by x momentum plus v multiply by y momentum and plus w multiply by z momentum. So, if these are the x momentum equation, y momentum equation, z equation corresponding multiply with the corresponding velocity, you will get this same expression in the for the total energy. Remember, energy is a scalar quantity. If you want to do in a vector form, you could do u dot your the vector momentum equation, okay, and you will get the same expression, right. So, once you do this, you can write it further. This is rho d, basically this is u I by 2 or u square by 2 by dt is equal to u I del by del x j tau I j plus rho u I b I. What is this u I by 2? You can denote it by the term k, which is nothing but your kinetic energy per unit volume, right, but kinetic energy per unit mass. Okay. So, you can write it rho dk by dt is equal to u I del by del x j tau I j plus rho u I b I, right. So, this is the basically kinetic energy expression. This is the kinetic energy equation. Now, one interesting thing is it is not a separate equation, okay. This we just took the momentum equation here, okay, multiply by u and we got this expression. So, and it does not have any temperature term involved here, right. So, the kinetic energy equation is not a separate equation, So, even if you include it in the, let us say, in incompressible flow solver, it will be kind of redundant equation, right. It is not adding any new information, right. So, we derived it because we want to go to the total energy equation, basically the kinetic energy plus your thermal energy, right, and you can have potential energy also, okay, but normally the variation of potential energy is not that high. So, we will just ignore it as of now, okay. So, you can write in the conservation form like this also. So, this d by dt of k will become dk by dt, okay, and then you can take this rho inside also. Remember how we have done for the momentum equation. So, you can use this equation of continuity, add it here, add and subtract here, and you can write in the conservation form. So, that rho goes inside, okay, and this will become d by dt rho k and plus d by dxj rho uj k, right. If you use the chain rule and then use the equation of continuity, you can get it back into this total energy form, okay, and right hand remains the same, okay. So, if you look at the different terminology, this d rho k by dt here is nothing but how the kinetic energy in the system is changing with time, right, and this is nothing but the transport of the kinetic energy. This is a kind of flux, okay. It does not, the only job of this term is basically to exchange the kinetic energy, or basically take the energy from one point to another point, okay. That is the job of this term. This is a very important term. This is the how the kinetic energy changes due to stress, right. So, if you have some stress in the fluid, okay, some viscous stress, so that will have the changes in the velocity, and that will basically change your energy. So, because it is in the right side, so if it is positive, then your d rho k by dt will be positive, right. So, this is increase in kinetic energy due to stress, and this is work by body force. Now, one point to remember here is that this is not the only thing which is changing due to the stress, right. In fact, if you want to take the total change in energy due to the stress, then it will be u y tau I j, okay. So, this is your total change in energy, and you can write it using the chain rule, basically, which is u y tau I j by del x j and plus tau I j del u I by del x j, right. So, this is the term which is responsible for increasing in kinetic energy, okay. Now, this term is related to the deformation, okay, and so this term would be related to the, because it is not changing the kinetic energy, but rather it is doing the deformation. So, this will basically increase the internal energy. So, if equation which involves both the kinetic energy k plus internal energy E, you will have both these terms, right. But for now you can just replace this term, okay. You can write this kinetic energy due to stress and increase in internal energy due to the deformation work, okay. And finally, what you can do, you can write your term which was your deformation work, okay, which is basically responsible for increase in kinetic energy into a more presentable form, because we know the tau I j. So, we can basically expand it. So, if you write tau I j del u I by del x j, it can be written in terms of symmetric tensor, basically this will be tau I j E I j. And why is that? Why, how can we write this gradient del u I by del x j is as a symmetric tensor? This is because of the property that if you have symmetric tensor, so tau I j is a symmetric tensor, multiply with another tensor, only the symmetric part is retained, right, and we can prove it also, right. Let me just prove it here. We have this tau I j del u I by del x j, right, and del u I by del x j is the standard tensor. It can be written as half del u I by del x j plus del u j by del x I, okay, and plus half del u I by del x j minus del u j by del x I, right. So, this is the symmetric part which have been denoting by the symbol Eij, okay, and plus this is the antisymmetric part which is nothing but half omega Ij, but just to for this multiplication purpose we will denote it by Aij, which means that this is an antisymmetric part, right. So, this is a symmetric part and this is an antisymmetric part. So, you can write it tau Ij Eij plus Aij, right, which can be written as tau Ij Eij plus tau Ij Aij, right. Now, tau Ij is symmetric. So, tau Ij equal to tau j I, okay. Eij is symmetric. So, Eij equal to Ej I, and Aij is antisymmetric. So, Aij equal to minus Aj I, right. So, if I exchange this j and I, okay, so we are allowed to do that, okay. So, that will become tau j I Ej I because they are symmetric tensor plus tau j I minus Aj I, right. So, this will become tau j I Ej I minus tau j I and Aj I. Now, remember this j and I, because of the repetition they are basically demi indices. You could also use Lm, Mn, whatever you think you want, whatever notation you want. So, you can further write it in terms of, if I replace I and j, this will become tau Ij Eij minus tau Ij Aij, right, because they are dummy indices, right. So, you can compare this A and B, right. So, left hand side is now the first term is same, but second term one is positive and one is negative, okay. This is only possible when you have tau Ij Aij is equal to 0, right. That means, your tau Ij del ui by del xj is nothing but your tau Ij into the symmetric part of the illustrated tensor, right. So, this is a very important result, okay, and we will be using it again and again at many places. I can interchangeably use either this term or this term, okay. And it also shows that if you multiply a symmetric tensor, okay, with an antisymmetric tensor, okay, that will go to 0. The product of a symmetric tensor with another an antisymmetric tensor is 0, right. So, if you use this relation, okay, so you can write this tau Ij del ui by del xj is tau Ij Eij, and you can further write this Eij as tau Ij, you can further write this tau Ij into our constitutive relation that we have derived, okay. By the way, so what constitutive relation that we have derived is for the Newtonian fluid, okay, where we say there is a linear variation of the stress due to the strain, but it need not be linear, okay. It can be quadratic or it can be other fluid also. So, accordingly you have to basically change your constitutive relation. Let us say you are working with some non-Newtonian fluid, Bingham plastic or shear thickening kind of fluid, then accordingly you have to basically change this tau Ij term. So, that is a very important thing that I want to mention here, is that your Navier-Stokes equation in terms of your mass into acceleration is equal to the stress term plus body force, that remains the same regardless of what fluid you are using, but what changes is your constitutive relation, that means how you relate your tau Ij to your standard tensor, okay, that changes and that depends on the fluid, okay. So, in the Newtonian fluid we assume it to be the linear proportionality constant is linear, which is the viscosity, but in other fluids you can have non-linear relations also, and you have to basically write that, derive that constitutive relation and use that in your code if you are developing a CFD code for a non-Newtonian fluid, okay. So, the tau Ij has got 3 terms, okay. So, that is hydrostatic, which is nothing but minus P delta Ij and plus deviatoric. So, deviatoric will have again have 2 term, one is that 2 mu Eij, okay, and minus 2 by 3 delta Ij del uk by del xk and multiply by Eij, right. So, this P delta Ij and Eij if you multiply is will become nothing but minus P del uk by del xk, right, because this Eij will only be true will be a number when delta ij is when I is equal to j, right. When I is not equal to 0, E I j will become 0, right. So, E I j will only be non-zero when delta I j is equal to delta I a or delta I j and delta j j, right. This will become 2 mu E I j and minus 2 by 3 del u k by del x k square. Okay. Now, this two term you can see, okay, this has got the viscosity term, okay, there will be mu here also and here also, because we are representing our viscosity, the second coefficient of viscosity in terms of the first coefficient of viscosity, assuming the Stokes hypothesis is valid, right. So, these two term together is the viscous dissipation term and we will denote it by epsilon, right. So, this will become minus p, you can write del dot u plus epsilon, okay, which is the viscous dissipation term, okay, and you can basically find out the unit of this dissipation term, okay. So, dissipation per unit volume in fact, okay. So, this is del u k by del x k, right. So, and there is a mu term here, okay. So, you can divide it by rho, that will become your kinematic viscosity and then you will have this term del u k by del x k term, which is the bulk viscosity. So, please go back and derive this unit for this dissipation rate and it will come out meter square per second cube, okay. So, once you do that, you can write this entire expression, the kinetic energy expression. So, what we will do, we will exchange this u I del tau I j by del x j by del u I tau I j by del x j minus tau I j del u I by del x j, okay. So, this term is the total work by stress, okay, which includes the work the change in the kinetic energy as well as the internal energy, but because this is just a kinetic energy expression, you have to basically subtract the term which is due to the internal energy change and that will be these terms, okay. So, what are these terms? This is the work by the volume expansion, okay, and this will only be true when the flow is compressible, because otherwise the del dot u will go to 0, okay, and this is your viscous dissipation term, okay. So, note that there is no difference between this expression this kinetic energy equation and the earlier kinetic energy equation that we derived, okay, this one, this equation, okay. We have only expressed this term into the total stress term, the total change in energy with due to the stress, and then I subtracted the change in internal energy, because this is only the kinetic energy expression, but this is not a separate equation, that you must remember. This is only we are taking the momentum equation, multiplying with the velocity and getting a new equation for the kinetic energy, okay. In the compressible flow, however, you will have change in both the kinetic energy as well as internal energy, okay. In that case, what will happen, you can write your total energy, okay, which will be E plus K, right. What is E here is basically your internal energy, and we want to find out an expression which gives you the change in internal energy as well as kinetic energy. And if the fluid that we are taking is assumed to be basically calorically perfect, then you can write it as CVT and plus half u square, right. And if you talk about this total energy rho E, that will be rho E plus rho K, right. This is as per unit mass. Now, what I am doing is per unit volume, so this will be rho CVT plus half rho u square, right. And now, what is CV? Equal to RT by gamma minus 1, okay. For the isentropic gas we had derived this, okay. So, this will be rho RT by gamma minus 1 plus half rho u square, and this can also be rho RT is nothing but P, okay, P by gamma minus 1, this is equation of state, plus half rho u square. So, you can write your total energy in terms of pressure or velocity, or in terms of temperature, density and velocity, right. So, what you can see here is basically you will have 5 variables here, rho, u, v, w, p, and then you will have another 6 variables, which is the change in temperature, but the temperature change is related to the change in density and the pressure, right. So, you do not need the 6th dynamical equation, but you can have 5 dynamical equation, which are basically, one is the mass conservation, 3 the momentum conservation, and the energy conservation, this becomes 5, and 6th one is the your equation of state. If the flow is compressible, if the flow is incompressible, okay, then you do not need an energy equation. You have the continuity equation, which is nothing but del dot u equal to 0, which is a constant in your velocity, and you can derive your pressure position equation from that, and plus 3 momentum. Okay, but we have only 4 thing u, v, w and p, which are the unknown variables in the case of incompressible flow. So, this is your compressible, okay, this is your incompressible. To express it further, you have 1 mass conservation plus 3 momentum plus 1 energy and plus 1 equation of state, right. So, 1, 3, 4, 5, 6. So, 6 equations and 6 variables done for the case of incompressible, 1 mass conservation, or you can call it pressure Poisson, okay. I mean, when it is expressed in terms of the dynamical equation of a pressure, plus 3 momentum, okay. So, total 4 equations and 4 unknowns, right. Now, it depends on what is the numerical scheme that we want to solve this, okay. So, without going into the too much derivation, okay, like we have derived for the kinetic energy, we just have to add the thermal energy component, and it follows your basically first law of thermodynamics, where we say that if we add any energy, it is basically used to expand or the work to be done on the system, okay, and the system will do the work as well as the internal energy will change. So, considering all those energy conservation laws, you can write your energy equation in this form, okay. So, here you can see it is very close to the kinetic energy form, except that there are 2-3 things. One is that here instead of k we have E, which is E plus k, okay, this E, and then instead of your the work due to the stress to increase the kinetic energy, we also have the increase in internal energy component. So, we are getting the total stress term here, and this is an additional term, okay, del q j by del x j, which is basically if there is a heat addition or something, you can use the Fourier's law here. So, that component needs to be taken care, okay. This comes directly from your first law of thermodynamics. This entire thing can be written also in terms of your separate part, which is basically your pressure part and your derivative stress part, okay. And you can take this pressure part on the left, okay. So, then it will become del by del x j rho u j E plus P, right, u j P, which is nothing but del by del x j rho u j, okay, E plus P by rho, right. So, if you look at this expression, this is nothing but your internal energy, kinetic energy plus your pressure energy P by rho, right. So, this is, you can write it in terms of enthalpy, right. Remember H equal to E plus P V, right. So, that E plus P by rho, right. So, you can write it del by del x j is equal to rho u j h, okay, by just taking your pressure term on the left side, okay, and then remaining terms are as it is, okay. And then you can use the Fourier's law. So, that will be q j is equal to minus k, which is k the thermal conductivity, del T by del x j, okay. So, you can express your thermal conductivity term in terms of your temperature gradient, right. So, from this what you can do, you have the total energy equation, okay. You can write in any form that you want. So, you can get an equation called the thermal energy equation. What is thermal energy equation? Basically, you want to subtract the kinetic energy term from the total energy term. So, that will be basically total energy minus your kinetic energy, okay, equation. So, if you do that, we have already derived the kinetic energy equation earlier, and we have also just saw the total energy equation. So, you will get an equation in terms of your just the internal energy, okay. So, you have this small is just the internal energy. So, we had this rho E and then we did minus rho K. So, that is rho E plus K minus rho K. So, you got this rho E. So, you have the expression for internal energy, okay. And similarly, you will have this convection term, convection of internal energy term due to the pressure, okay. This is due to the expansion or contraction, okay. And then of course, so what was positive here, del Q j by del x j, okay. Okay, this is minus del Q by del x j, and plus this is the viscous dissipation term that we have derived in the kinetic energy equation, right. We had two terms in the first coefficient of viscosity, second coefficient of viscosity. So, this is the viscous dissipation term, okay. So, what it says is that internal energy increases because of the convergence of heat, okay. This one, okay, the volume compression, which is this one, okay, the compression or expansion whatever it is, with this expansion then the internal energy will decrease, okay. And last one is the heating due to the viscous dissipation, because of dissipation the heat will increase, okay. So, this is your thermal energy expression. So, equation. So, in some of the codes you may use the total energy equation, in some other codes you may use the thermal energy equation. For example, in many pressure based solver the thermal energy equation is employed, but in the compressible solver usually you consider both the total thermal energy as well as the kinetic energy, okay. And this is the last approximation, okay. We can use the Boussinesq approximation, basically typically valid for low speeds, okay. Basically if the flow speed is not very high and the dissipation, then in that case will not be very high, okay. So, what you can do, so the earlier equation, this equation can be written as rho dE by dt, okay, in terms of total energy term is equal to minus P del dot U minus del Q j by del x j and plus epsilon, right. This left term I expressed in terms of completely the total derivative, and dissipation goes to 0, okay. And we can absorb this term on the left minus P del dot U. So, this will become rho d h by dt, okay, where h is the enthalpy now, is equal to minus del Q j by del x j, right. And then you can write this h equal to C p t, right, for a calorically perfect gas. So, then you can write this expression as rho C p dH by dt is equal to minus del Q j by del x j, and if you use the Fourier's law, okay, so then it will become K del 2 T, okay, by del x square, okay. You will have all the three terms, okay, plus del 2 T by del y square plus del 2 T by del z square, right. This is your term, and you can take this on the rho C p on the right side. So, this is rho C p dH by dt. So, dH by dt will become equal to K by rho C p into del square T, right, where K by rho C p can be written as kappa, okay, which is nothing but the thermal diffusivity, okay. So, we saw many different forms of the equation. We saw the kinetic energy equation, also called the mechanical energy equation there. You can also include the potential energy term there. We saw the total energy equation, where we have both the kinetic energy plus your thermal energy, and then you can write in terms of thermal energy equation also, where you need not consider the kinetic energy equation, and in the Boussinesq limit basically for the low speeds where the dissipation can be ignored, we can get a very simple form which is dt by dt. Okay. 0 Cp dt by dt. Okay. So, you can write the equation for temperature here in the Boussinesq limit. Okay. So, with that we will stop here. In the next class we will see how we can write this entire equations in the matrix form, so that it is easy to solve it in a coupled manner. Okay. Let us say we want to solve both all the mass, momentum, energy together. It will be good to write in a form where you can take the temperature terms together, the advection terms together, the dissipation terms together, and so on and so forth. Okay. So, we will look at that in the next class. Thank you very much.